What if the biggest limitation of today's AI models isn't their size or their training data, but their memory? What if they literally forget everything the moment a conversation gets long enough? Researchers at Google just introduced a fundamentally new kind of memory for AI, one that learns what to remember and what to forget in real time. Here's the core challenge. Transformers, the architecture behind ChatGPT, Gemini, and every major language model, process text by comparing every word against every other word in a conversation. That works beautifully for short conversations, but the computational cost grows quadratically. Double the input length, and you quadruple the work. That means real-world tasks like analyzing entire books, long videos, or genomic sequences become impossibly expensive. Previous solutions tried to fix this with compression, cramming everything into a small, fixed-size memory. But compression means losing information. It's like trying to summarize War and Peace in a single sentence. Critical details vanish. The AI field has been stuck. Accurate models that can't scale or scalable models that can't remember. Something fundamentally new is needed. The researchers found their answer in how the human brain actually works. We don't store every detail equally. We remember what surprises us, and we gradually forget the rest. They built a neural long-term memory module, essentially a small neural network inside the larger model. It runs alongside the main attention system, continuously learning to store important information from the past. Here's the key insight. This memory module measures how surprised it is by each new piece of information. If something is unexpected, if it violates the model's predictions, it gets written deeply into memory. Routine information fades away naturally. They call this the surprise metric. It's calculated using the gradient of the memory's own loss function. A large gradient means the input is genuinely new and worth remembering. This gives the model an elegant, self-regulating memory system. The architecture they built around this, called Titans, combines three types of memory: short-term attention for the current context, long-term neural memory for the distant past, and persistent memory that stores general knowledge about the task itself. Think of it like this. Attention is your working memory. The neural memory is your life experience, and persistent memory is your general knowledge. Each operates independently but works together seamlessly. And crucially, the whole system can be trained in parallel, making it practical for real-world scale. The results are striking. On standard language benchmarks, Titans with just 340 million parameters outperformed every competing architecture, including Transformers, Mamba, and gated DeltaNet. The neural memory module alone beat all non-hybrid baselines. On common-sense reasoning tasks like PQA and HelloSwag, Titans achieved the highest scores across the board. At the 760 million parameter scale, the memory as context variant reached over 49% average accuracy, a clear lead over all competitors. But the most dramatic results came in long context tasks. On the needle in a haystack benchmark, where models must find a specific fact buried in millions of tokens, Titans scaled to over 2 million tokens with near-perfect accuracy. That's not a typo. 2 million tokens of context. For comparison, most transformer models struggle beyond 128,000. Titans didn't just match the competition at long range, they left them behind entirely. The results extended beyond language, too. On DNA modeling tasks for genomics and long-range time series forecasting, the neural memory module matched or exceeded state-of-the-art specialized architectures across every benchmark tested. This research points toward a future where AI models can process truly unlimited context, entire code bases, full legal depositions, years of medical records, without the crippling cost that makes today's long context models impractical for most applications. For researchers, Titans offer a compelling new paradigm. The surprise-based memory mechanism is mathematically equivalent to mini-batch gradient descent with momentum and weight decay, connecting memory theory to well-understood optimization principles. Open questions remain. How deep should the memory network be? Can this approach work for vision and multimodal tasks? And what happens when you scale Titans to tens or hundreds of billions of parameters? The lesson from Titans is simple but profound. AI doesn't need to see everything at once to understand it. It just needs to learn what's worth remembering. This is Titans from Google Research.